This is an AQA A-level chemistry topic. It's year 13, organic chemistry. We're looking at amines. As always, I'm going to recommend you pause, have a go at the activities, and then review. So, in this final video in this topic, we are going to look at ammonia and amine in their capacity as nucleophiles. We're going to see how haloalkanes react with ammonia and amines, an extension of work in year 12. We're also going to look at how we can make amines from nitriles, and we're going to do some work on aromatic amines and how we make those from benzene. So let's begin with something that you are hopefully quite familiar with from year 12, and I want you to have a go at completing this mechanism to show the reaction of ammonia with 2-bromobutane. Well, we have got our lone pair on the nitrogen, so that's where our arrow is going to begin, and it's going to be attacking the delta positive carbon. This is delta positive because the bromine is delta negative. That's the difference in electronegativity. So, curly arrow going into the carbon. That creates a bond between the carbon and the nitrogen, which means we need to break the CBr bond, so we have an arrow from the pair of electrons to the bromine. That takes us to our intermediate, and our intermediate looks like this. My bromine has essentially been replaced with an NH3+. I've got my Br- that's been given off as the secondary product there. So not stable, but we're going to deal with that in a few minutes. The thing is, this as an intermediate is not stable either. To deal with it, we add some ammonia, another ammonia, but this ammonia does not act as a nucleophile, it acts as a base. It's going to attack one of the protons on the NH3+. It takes that away, which means that these electrons are going to move in to the N, and that's going to discharge this positive charge here. That takes us to our amine. This is a secondary amine, 2-aminobutane, and we've also got an ammonium ion, NH4+. Now the NH4+ and the Br- will combine to make ammonium bromide. The type of reaction, going back to year 12, the type of mechanism I should say, is nucleophilic substitution, and I've already said that this is 2-aminobutane. The thing is, where we stopped in year 12 is not really the end of this reaction. We actually know from the previous video that primary amines are stronger bases. So that would mean actually the amine we have just made would be an even better proton acceptor. That means it's going to be a better electron donor, means it's going to be a better nucleophile. So for the next few mechanisms, we're going to take ethylamine acting as a nucleophile instead of ammonia with chloroethane. We are still going to use ammonia in the second stage of this mechanism each time, and that's a really important thing to remember because otherwise it can sow quite a lot of confusion. But let's look at the mechanism, try it, see how you do. Here's my chloroethane and here is my ethylamine. I'm drawing it in a very similar way to how I drew the ammonia earlier on. My lone pair is going to attack the delta positive carbon. That's going to cause the CCl bond to break. Those electrons move to the chlorine here, and that takes us to the intermediate. Now the intermediate that we've got, you can see my N with my 2 H's, my C2H5. I'm not finished. I've not got the intermediate mark yet, and that's because this nitrogen is positive. And also you can see there that we have made a chloride ion as well. The Cl- has been lost. As we saw previously, we don't stop at the intermediate, we take another ammonia. This ammonia acts as a base, it attacks one of the hydrogens on the nitrogen. That's going to cause the NH bond to break, those electrons move in, discharging the nitrogen. It's an identical mechanism. The only difference to what we saw earlier is this is a C2H5 instead of an H. Now that takes us to our final product, and you can see here we've got the N, we've got 2 C2H5s coming off, we've got an H, and we've made NH4+. But again, the NH4+ and the Cl- will combine to make ammonium chloride. But it doesn't stop there, because I've now got diethylamine, which can act as a nucleophile. So have a go at the mechanism that reacts diethylamine with chloroethane. And on this one, you can see again, I've written it in exactly the same format. My ammonia, 2 of the H's have now been replaced by C2H5s, but essentially the same. My lone pair attacks the delta positive carbon. The CCl bond breaks. My electrons move towards the chlorine. I go to my intermediate, looking a little bit more complicated now. Remembering once again that this nitrogen is positive. So I'm going to need to stabilize that. I'm going to add ammonia once again. The ammonia acting as a base is going to take this hydrogen, which is going to cause the NH bond to break, electrons moving in to discharge the N. I've also got a chloride ion made. That then takes me to the product. I've got my N with a lone pair now surrounded by 3 ethyl groups, and I've also made an NH4 plus ion. The NH4 plus and the Cl minus combine to make ammonium chloride. But I've still not finished, because this can act as a nucleophile, the tertiary amine. So what would it look like when triethylamine acts as a nucleophile with chloroethane? Well, let's draw out the chloroethane and let's draw out our triethylamine, following exactly the same format because it's exactly the same mechanism. My lone pair attacks the delta positive carbon, the CCl bond breaks. That takes us to our intermediate, and you can see here that I've now got the N surrounded by 4 C2H5s and the Cl minus is given off. And I've got my plus here. This is where there is a slight difference. We have made a quaternary ammonium ion, and that can combine with the chloride to make a quaternary ammonium salt. That's actually where this mechanism ends. Doesn't go any further. So now we need to think a little bit more about the chemistry that we can learn from that. First of all, let's imagine that you were making amines. Would you use the method of nucleophilic substitution or not? Why would you make that choice? So the reality is it is not used industrially. The reason it's not used industrially is you actually get a range of different products. You don't get one final product at the end of this. You might get some primary, secondary and tertiary amines and quaternary ammonium salts. But if you did do it industrially, there are factors that you could alter, that you could change, that would maximize your chance of one product over another. What could you do to minimize the formation of actually quaternary ammonium salts and maximize the formation of quaternary ammonium salts? Well, let's start by drawing them out. We could go from ammonia all the way to the quaternary ammonium salt. If I wanted to minimize substitutions, I'd make sure I started with lots of ammonia, because then there would be a greater chance that each chloroalkane or haloalkane that I added would go to a different ammonia. So an excess of ammonia will minimize multiple substitutions and is more likely to take you to the primary amine. But if I've got a very small amount of ammonia or a large excess of a haloalkane, then that haloalkane is going to keep adding on around the nitrogen, multiple substitutions. So if I wanted to make my quaternary ammonium salt, I would use an excess of the haloalkane. Really common question in the exam. You do need to be prepared for that one. Now, we do need to use quaternary ammonium salts. They're very useful as cationic surfactants. What does that mean? Where do we use them? Well, we use them in hair conditioner, fabric conditioner, and what can often happen when you have wet fabric or wet hair is you can get negative charges start to build up on them. You start to get static electricity, so your hair might start to stand on end, as an example. These cations, the cationic surfactants, the quaternary ammonium salts, actually form a coating that prevents that static electricity building up, so you don't get that flyaway hair. You don't get that build-up of static electricity in the clothing. So what about alternative methods of amine production? We've talked about the limitations of that method, that we can't specify one specific product, even if we can maximise potential of one over the other. But you did a mechanism in year 12. I want you to think about how you can do that using potassium cyanide and 1-bromoethane. What are the reagents? What's the nucleophile? What type of mechanism is it? And what are the industrial advantages of this method? Let's start off with our mechanism beginning. You will notice, even though we're using potassium cyanide, it's Cn- that goes in the mechanism. Don't get that mixed up. The Cn- is going to attack the delta positive carbon. That's going to cause the CBr bond to break, and that takes us to our nitrile, propane nitrile here with our Br- ion. The reagent is KCN. The nucleophile is Cn-, a really important distinction. The nucleophile is what does the attack. The reagent is how it comes in a bottle. You can't get a bottle of negative cyanide ions. They have to come within a compound. Advantages. 1, this extends the carbon chain in a controlled way. I've gone from bromoethane to propane nitrile. In industry, that's a really important thing to be able to do. But what else? Well, it takes us to one specific product. We've made propane nitrile. And as we're considering how we can take this forward to make an amine, that means that we can make a specific amine. So let's take a look at that stage now. If I take my nitrile, this is actually butane nitrile now, I can add hydrogens. Now they are in square brackets because they are coming from LiAlH4 in dry ether with water. Alternatively, you can do it as 2H2 hydrogenation in the presence of a nickel catalyst. But it means that I can do in a two-step process from a haloalkane to a nitrile to an amine. And I can guarantee the amine I'm going to make. It's going to be primary. We do use NaBH4 as a reducing agent elsewhere, but we don't use it here. Why is that? Well, it's actually because it's not a powerful enough reducing agent. What about the formation of aromatic amines by the reduction of nitro compounds? This comes straight from the aromatic topic. Can you remember the mechanism that shows the formation of nitrobenzene? So we have got, that's an H there, that's badly written. H2SO4 plus HNO3 goes to HSO4 minus to H2NO3 plus. But the H2NO3 plus breaks down into H2O and NO2 plus. At that point, I can begin my mechanism. My NO2 plus is attacked by the electrons in the delocalized ring. That causes this intermediate to be produced. More details on the specificity or the specifics of this mechanism in the aromatics videos. But I've got my broken ring, I've got my NO2 added, and I'm now including my H. I've got to include the H because it's the electrons from the CH bond that move in to regenerate that ring, making the nitrobenzene. Why is nitrobenzene important? Well, it's nitrobenzene that's then used to make the phenylamine. I can add 6 H's, and I do that to get to my C6H5NH2, but I also make 2H2O. What are the conditions for this? I do it with tin in the presence of HCl. And finally, to bring us to the end of this video, pure phenylamine is used to make dyes in the dye industry. It isn't a dye itself. That's something that's come up in multiple choice questions from memory once or twice. Amines in acidic solution form salts like phenyl ammonium chloride. So write an equation to show how NaOH could free the amine and enable it to be extracted as a pure phenylamine. So a good thing to remember here, a good thing to be able to do. Here is my phenyl ammonium chloride. I'm adding NaOH, and I go back to my phenylamine, and in doing so, I'm also making H2O and NaCl. So that takes us to the end of this video and the end of this topic. Thank you for listening, and goodbye.